use this theory about the small world that we just described. So the question is, how can we then apply this theory, these ideas from this experiment that everyone in the world is closely related, and try to use that to make this network where people only have to talk to their trusted friends? And the first thing we need to realize is that in order to do this, we need to have some way of accessing information in the network. And in the old freenet, in the old peer-to-peer networks, where computers would talk to each other at random, and you didn't have any control over who your computer was talking to, you could just go on somewhere on the network and grab the file from somebody, or look up in an index or whatever. So they're always building links between computers. But in this case, we don't have that. We only have this social network of people and their friends to find something. So we need a way to look through this social network in order to find data or find things on our network. So in other words, we need a way to route through the network just like one would on the internet. And on the internet, of course, there's a system of routing which depends on IP addresses and all that kind of stuff, where the IP address tells you which network it belongs to and then what host on the network. And this is a very hierarchical system that then allows you to route onto the thing. But, and these numbers then are assigned according to some plan. There's a whole plan of people who actually assign internet addresses so that the system works. Whereas in our case, we have this social network which is completely unplanned, completely chaotic, yet we have certain properties, and we want to find some decentralized way of searching in this network so that we can find the data we're looking for in the dark peer-to-peer network. And of course, Ian just described that we had this Milgram experiment where people were given a letter and they were asked to forward it by only sending it to acquaintances. And it turned out that this is pretty much exactly, this is pretty much exactly what we want to do in the dark network. We have a network that's set up with links only between people who know each other, and we want to be able to send a message from one side to the other in order to access some data or communicate in some way. And so if people were able to do this, they were able to find a way to send this letter to the correct person, even though he was on the other side of the United States, then we could hope that there is actually a way that computers could do this as well, just perhaps, in seconds rather than days, because we want it to be useful. And to do this, we have to look at what are the dynamics, what is the mathematical situation in a network which allows this to be the case. And this goes back to the small world properties that Ian was talking about. And in particular, there's an explanation by a computer scientist, John Kleinberg at Cornell, who showed the kind of dynamics that a network needs to have in order for it to be possible for this type of greedy routing to actually find paths quickly. In order for it to be possible in this graph to just say, okay, we need to go in that direction, and then we just try to always go as near as we can, and hopefully we'll find the thing in a short number of steps. So it turns out that the possibility of being able to route possibly depends essentially on this property that there are connections of different lengths. Most of your connections are to people who somehow surround you, your neighbors, your close friends, who then somehow are near you in some overlying space. But sometimes there are long connections that go far away. So somebody in Germany has a friend in New Zealand or Brazil or something, so that we can make long steps, but most of them are short, so that once we get close to somebody, it becomes more likely that they actually know the person that they are near. And there needs to be a very specific relationship between the amount of short and long edges of different lengths in order for this type of routing to be possible. It needs to be that as you get further and further away, the probability that you know someone will decrease, and it has to be that the probability of these links or friendships occurring has to be inversely proportional to the length of the friendships. And in that case, we actually have this simple greedy routing where we just say, okay, we have a position, we want to go somewhere, well, we'll just send it to the right person, and we'll just send it to the person who's closest to our destination, and then it should get through in the steps that are about on the order of log squared of n, which is usually pretty good in these types of situations. Anything that's log tends to be good. But the problem is, of course, that this greedy routing depends, you want to say, okay, we're going to make it go closer, but we're dealt here a completely social network. We're told who knows who, because each node in the darknet knows which his friends are, but we have no idea about where people are, about who they were. We can't say that sort of thing. So there's no easy way to answer if the person is closer to another. There's no easy way to answer these sort of questions, which we end up having to ask. We know we want to send a message to Harry, and I have two friends, Alice and Bob. And the question is, of course, if I want to apply this greedy routing, I should just send to the person who's closest to Harry in some sense. And that sense might be geographic sense, or it might be, but just I want to send it to who's the most likely to know Harry. And this is not a question which directly has an algorithmic answer. So if you go back to the experiment that people did where they're sending letters, and you actually have this letter, and you know it needs to go to Harry, and you're trying to decide if you want to send it to Alice or Bob. Well, you might look at where do they live, what do they do, what do they work with, and try to see which of those two is going to be the closest to Harry. But in practice, when we ask the computer to do this, we can't really do this. And there are several reasons for this. For one, it's rather impractical to try to think of a metric that the computer would use to try to see how similar are two people. And for the other thing, of course, we have to remember that our thing here is that we want to build this anonymous file sharing network. And with our users, if the first thing that happens when you install it is, oh, would you please insert all your personal information so that we can route, they won't be very happy. So we can't really do that. So instead, what we have to do is we have to take the network, which is all that we've been given, and use that to tell us where people belong in the world's social space, and then we can route based on that. So we're going to show this in a second so that you get a very clear visual idea of what we're doing, but just to outline it first. What we know is that this model of how a navigable small world network looks is that for this to work, there needs to be few long connections and many short ones. And sort of as the connections get longer, they need to get less and less likely to occur. So people who are far away from each other need to have few connections between each other. People who are close should have many. So what we try to do is that when people join this network, they're given a position or a numerical identity. And this is assigned in some grid. And then we try to assign these in a way so that we actually get this property that people who are close together conceptually in the world's social space somehow, people who are likely to know each other, will end up close together, whereas people who are far away in the world's social space in some way end up far apart in this thing. And then, so another way of looking at this is that we have the world. So in some sense, there is some space which everyone in the world belongs to, and mostly maybe geographic. You know, you tend to know people who are close to you, who live in the same city or in the same country. But there's also the other things, like you tend to know people who do the same thing, who might come to Chaos Computer Club meetings or something like that, even if they're from far away. So we need to try to reverse engineer these positions of people in the world based only on what each person knows, and we need to do it in a decentralized way because all the time we don't want anybody to have global information. Everyone has to, at their point, just do some calculation and decide where they should be. And once we've done this, then we can return to the greedy routing case and just say, well, now we have positions, and if we want to find somebody, we just have to, they have an address that we can just route to by just looking at our neighbors and saying, well, which one is closest to the destination? And that's where I'll send my message for them. So in general, there's a very simple algorithm to do this, which is when people join the network, they're given a position at random. So at first, everyone just chooses a position at random. And this will result in something very unoptimal, because if you've just chosen a position at random, you and your best friend, who would be likely to know many of the same people, might still end up on the opposite sides of the network. But then there's a switching algorithm by which people switch their positions, and they switch positions with other nodes, and we do this in a way so that the people try to see, so that people who are close to each other in the world's social space should end up close to each other in their identifiers. And now we should try to run this graphical demonstration so you can see this in practice.
This is the fun bit, hopefully.
So everyone who's asleep can wake up.
Wake up. Okay, so let me just explain what you're looking at here so you understand what's about to happen. We have a network here. It's a 15 by 15 network. where we have a bunch of nodes. Some of these nodes are connected to each other, some of these nodes are not. So if you imagine each of these nodes is a person, each of the lines you see connecting nodes is a friendship between those people. Or more accurately, each of these nodes is a freenet user. Each line between freenet users are people who trust each other and who have a direct connection between each other. Now, we have arranged this network such that it has a small world structure according to what Kleinberg tells us the small world structure needs to be. And you can tell that because here at the bottom, we have a histogram which shows the number of links of each length. So you can see that we have a lot of very short links, and as the links get longer, we have fewer and fewer. And that actually corresponds pretty much exactly to what Kleinberg mathematically tells us is an optimal small world network.
So even though this is randomly generated data, it's randomly generated using the dynamics that we expect a social network to have, which is that each node here, that's these points that are connected, represents a person. And in this very, I mean, this isn't small world, this is a tiny world since it's only 15 by 15, but that's only because we can only show so much. The point is that people who are close together here will tend to be friends more often, because being close together on this represents being neighbors or being people who belong together somehow in the world. So we have this density of most people who are next to each other will know each other, but people on opposite ends of the thing will most probably not know each other. There are fewer people who know each other far away. And this is the kind of dynamics which you can see if you take a look at real social networks. This is the kind of thing that you have. Of course, you might not have, what you might not have is where the points are, which brings us.
So, what's good about this, what Kleinberg tells us, is that in this kind of network, greeting routing works really well. And if I do that, you can see what we've tried to do here is starting at the top left, we've tried to route down to the bottom right. And you can see that just using greedy routing, you can see that that actually happened in just 1, 2, 3, 4, 5, 6 steps. So that's pretty good. So this well, it doesn't prove anything, but it shows that in this kind of small world network, greedy routing works really well and can typically get from A to B quite quickly.
Yeah. So there's no cheating going on here or anything. We just taken 2 points and we try to find a route between them. And at every step, it's just taking the neighbor that is closest to the destination according to this grid. And there's no. So, and you can see that, in fact, here, it seems to be a very good route, because at every step, it's getting closer and closer to the destination, which is the sort of what you would expect, because the dynamics of this network actually makes this sort of routing very effective.
So what we're going to do now is screw up this network, I hope. Okay. Now, it's very important to note that this is the same network. We haven't disconnected any nodes that were connected, and we haven't connected any nodes that were disconnected. It's the same network. All we've done is we've randomly rearranged the positions of all the peers in this network. And you can see the effect that this has on the histogram. Instead of the nice small world histogram where it started high on this side and went down, now we've got what is essentially a random distribution here.
And this represents sort of what we're given in the beginning with our dark network, because while we are given this sort of network of people's connections to each other, we don't have this global overview knowledge that we had before of who belongs next to whom. So we end up just having a graph which we've just thrown in the positions randomly to begin with, and it will look like this, where you don't see this dynamic of people being close to each other, being more likely to know each other. In fact, we have edges going all over the place because we just didn't know where people were supposed to be.
This is basically when freenet starts, this is kind of what it has. It knows who's connected to who, but it has no idea what their locations are. It has no idea who should be closer to who else in order to achieve a nice small world architecture. And we're going to prove that this sucks